In this video, I will go over the homework that follows the lecture 8.2, focusing on the integration by parts for definite integrals. And before we dive into the homework, I just want to remind you that I hope you watched the lecture before doing the homework, as I will be referring to some of the ideas and concepts as assuming that you are familiar with them. So let's go ahead and jump right into the homework. The first problem is right in front of us. It's an indefinite integral. Sorry, it is a definite integral. And one approach to definite integrals is to hit the pause button right away. So it's going to be a giant pause button. And say, hey, we don't care about the definite part of it. We are still concerned whether we can do the indefinite integral. And this would allow us to just focus on indefinite integral without worrying about how to write the limits and change the limits if we have to. So in such a case, we start by writing an indefinite integral, and then we proceed as before. We recognize this pattern. We say, hey, this is perfect for integration by parts. So my u will be arc cosine of 9x. My dv will be 1 dx, so that my du is going to be negative 1 over square root of 1 minus 9x squared. This is just the chain rule, and we multiply by the derivative of 9x, which is 9. And to find v, we just integrate that, so v is x. So in this integration by parts, we continue by writing out uv, so it's x arc cosine of 9x minus integral of v du. So v, and I'm just gonna take out this negative in the front. We have 9x over square root of 1 minus 9x squared dx. And the question is now, do we know how to do this integral? This is the time again where we have to decide what are we going to do here. So we may want to hit another pause button, not as big as the first one, but we do need to pause the solution thread here and ask ourselves, what are we going to do here? And the only thing that we can do here is substitution. So we're going to set up substitution. And again, I'm only talking about this integral, right? So the expressions outside of the integral are not affected by any of this. So we're going to set up substitution, and my substitution will be t is equal to 1 minus 9x squared. So that means dt, I'm doing substitution, right? It's going to be negative 81 so we have to be careful here, right? So t is 1 minus 81x squared. So dt is negative 162x dx. And let me get that substitution notes out of the way. So this is my substitution. So everything that I'm writing here only applies to this integral. So we have now, I guess it's worth saying that x dx will be negative 1 over 162 dt. And now my integral, so this integral, becomes integral of 9. So instead of x dx, I'm going to write negative 1 over 162 dt. And in the denominator, I have now square root of t. So simplifying this problem, and I guess we can squeeze it in here. What do we have? We have 9 goes into 162 18 times. So we have negative 1 over 18, but I'm going to write it like this, just so we can see the pattern. So this integral is pretty straightforward. It's just the integral of square root of t. But remember, t is not the original variable, x is. So here's my answer to this problem. So now it's time for us to hit the play button for that second pause that we did, and we're going to continue with our original solution. So we have x arc cosine of 9x minus 1/9 square root of 1 minus 81x squared plus c. So this is the answer to the indefinite integral. So we finished the indefinite integral problem. However, let's not forget that the original question was definite integral. So now we're going to continue the main thread of the solution. So this is a play button, and we're going to continue by applying the fundamental theorem of calculus. So now we have x arc cosine of 9x minus 1/9 square root of 1 minus 81x squared, and all that evaluated between 0 and 1/9. So we're plugging in 1/9, so we have 1/9 arc cosine. 9 times 1/9 is just 1. 1/9 squared is 1 over 81. 1 over 81 times 81 is 1. So 1 minus 1 is 0. And we now plug in 0. So 0 times anything is 0. And we have 1 minus 1/9 square root of 1. So this is kind of the finish line. We just need to figure out what's arc cosine of 1. In other words, cosine of what angle is equal to 1, and the answer is 0. So we have a lot of zeros here, except the last one. So this is 0, this is 0, this is 0, and the only non-zero is the last term, so negative times negative makes it positive. So the answer is 1/9. Now, this is absolutely valid approach for long solutions like this. Do the indefinite integral first, and then do the fundamental theorem of calculus at the very, very end. However, it is possible for us, once we get more experienced, to carry out, so let me write here, alternatively, we can carry out all those limits through as we're solving the problem. Usually that's more appropriate when you know what your solution is going to look like, so it's just a matter of you writing it out. So the first step here was integration by parts, so we're going to do that real quick here. So let's set it up, let's announce it. We do integration by parts. U is equal to arc cosine of 9x. dv is dx, so du is negative 1 over square root of, and we've done this earlier, so I'm just going to write the answer here, and here goes 9, and here goes dx, and v is just x, And now when we do integration by parts for definite integrals, we write out our uv, but we don't just write out uv, we start using the fundamental theorem of calculus. So here goes 0 to 1/9. So we're plugging it in right away. Minus, now we're not writing it as an indefinite integral, we keep writing those limits from 0 to 1/9. And the result here is uv minus integral of v du. So this still becomes plus. So what goes inside is still pretty much the same. So if you compare these two solutions side by side, you'll see how they are very similar, except in one case we write everything as an indefinite integral, and in another one we keep track of all the limits of integration. Here we're going to do substitution, just like before. And the substitution is the same. T is equal to 1 minus 81x squared. dt is equal to negative 162x dx, meaning that x dx is negative 1 over 162 dt. But again, this is a definite integral, and we want to change these limits of integration right away. So we're going to go from the limits for x to the limits for t. So when x is equal to 0, t is equal to 1, and when x is equal to 1/9, t is equal to 0. So those are going to be my new limits of integration. Now, again, remember, we're not pausing anything here. We're just doing everything in one continuous line. So now we're applying the fundamental theorem of calculus here. So we get 1/9 arc cosine of 1 minus 0 times arc cosine of 0. So that part is done. And now we're continuing with this integral. So we have new limits of integration from 1 to 0, but the variable is now t. So we write 9 x dx is now negative 1 over 162 dt. And in the denominator, we just have square root of t. So notice how at every step we're doing something, right? So arc cosine of 1 is 0. So here we have 0 minus 0. So there's nothing really there. And here we have now, we're going to take out negative 162. But we're going to divide 9 into this, so it's going to be negative 1 over 18. Integral from 1 to 0 of 1 over square root of t dt. And if you notice the pattern here, we can just throw extra 2 over here, extra 2 over here. So now we know the antiderivative there. So it's going to be negative 1 over 9. Square root of t is my antiderivative, but remember, it's a definite integral. So we evaluate it at the given limits. And finally, we just plug it in. Square root of 0 minus square root of 1. And the answer is 1/9, which should be the same as we got originally. Now, this looks nice and clean and pretty streamlined, only if you can carry all those transformations to the limits and apply the fundamental theorem of calculus to everything that comes out of the integral right away. If you can't, then this is a valid alternative. You do your integral as an indefinite integral, and then at the very end you just throw the limits of integration. I probably now personally prefer the latter one because of just how nice and clean it looks at the end. But you can have your own preferences. So the answer here is just 1/9. And we can see what Newton's preference is. Let's see. See, they like this U substitution, so they're doing something even crazy, right? So they don't do substitution, change of limits for substitution, which kind of takes away the benefit of writing out the solution this way. Anyway, I like it. Hopefully you like it too. Now it's just a matter of you learning how to write it all out carefully. So let's continue to the next problem. Problem number 2. We have integral from 0 to 4 x e to the power 3x dx. We're going to do integration by parts. I'm going to announce it here. So my u is x, my du is dx, my dv is e to the 3x dx, and my v is the integral of this, which is 1/3 e to the 3x plus c, but we can set c equal to 0. So if you don't know how to go from this dv to v, it's just a simple integral with a substitution, linear substitution, t equals 3x. Now we're gonna write uv out, so we have 1/3 x e to the power 3x. Now it came out of the integral, so we're gonna evaluate it, minus integral from 0 to 4 of v du. So again, this is not my first time doing it, so I know kind of how to simplify and do basic maintenance as I'm writing out the integral. So I'm going to write integral of v, 1/3 comes out, du, so it's just e to the 3x dx. Now, doing multiple things at once here. Plugging in 4 here, plugging in 0 in here, but we still have to worry about this integral. So antiderivative of that is 1/3 e to the 3x, and the limits of integration are from 0 to 4. Again, doing multiple things at once. So this is 0, this is just 4/3 e to the power 12, minus 1/9, and here we have e to the power 3x, but we're going to start evaluating it at the limits of integration. So it's going to be e to the power 12 minus e to the power 0. So the final answer is 4/3 e to the power 12 minus 1/9 e to the power 12 plus 1/9 e to the power 0, which is just 1. So if you want to simplify this, you can do common denominator. So we have 11/9 e to the power 12 plus 1/9. This is the final answer. So 11/9 e to the power 12 plus 1/9. All right, another one. We're going to set it up as an integration by parts. And I'm going to announce it here. U is going to be ln of 3x cubed dv will be 3x cubed dx. So du, it's the reciprocal of 3x cubed times the derivative of 3x cubed, which is 9x squared, which after you simplify it is just this. And v is just the antiderivative of that, so it's going to be 3x to the 4 divided by 4. So this is my setup. So now we continue with the solution. So we have uv, so it's 3/4 x to the 4 ln of 3x cubed evaluated from 1 to 4 minus integral from 1 to 4 of v, so 3x to the 4 over 4 du, which is 3 over x dx. And now we're gonna start working on evaluating it. So we have 3/4, we have 4 to the power 4 ln of 3 4 to the power 3 minus 1 to the power 4 ln of 3 times 1. So that's that part minus, and now we have to simplify this. So we have 9/4 x cubed, but antiderivative of x cubed is x to the 4 over 4. And we're applying the fundamental theorem of calculus right away. So again, working out, so we're kind of like at different stages of evaluating the integral depending on which part of the integral it is, but it's just a matter of writing things out carefully. 4 to the power 4 is same as 2 to the power 8, so it's 256. 4th cube is 64. 64 times 3 is 192. And I feel like there's got to be a way to simplify it. We're not getting nice numbers here at all. So here we have 9 over 16, and we're evaluating at x to the power 4, so we have 4 to the power 4 minus 1 to the power 4. Let's try to simplify it just a little bit. Now that this is not that important, let me make it smaller. And hopefully I don't make a mistake while I'm simplifying it, because that's also a possibility. But here we have 256 divided by 4, that's 64. So we have 3 over 64 ln of 192 minus 3/4 of ln 3. Now 4 to the power 4, that's 2 to the 8. 16 is 2 to the 4. So it's 2 to the 4, 16. So we have 9 times 16, which is 144. And we have plus 9 over 16. So I don't even know if I made it any simpler, but let's plug it in. So we have 3 ln of 192 divided by 64 minus 3 ln 3 divided by 4 minus 144 plus 9 over 16. I kind of had that feeling that this is going to happen. Let's check our work. So I'm checking my integration by parts right now here, setup. And it looks good. Minus integral, so now I'm at this line. Integral of 9/4 x cubed x to the 4. That looks fine too. So we have 3/4 uv minus v du. That looks fine too. So here I'm at the next line. It could have been me trying to simplify it too much is an issue. What's 4 cubed times 3? 4 times 4 times 4 times 3 is 192. 4 to the power 4 is 256. Divided by 4 is found it. So this is not 3/64. This is actually 3 times 64. So let's see. 3 times 64, it's 192. So that's the typo I found. Hopefully it's the only mistake, because I don't want to redo this problem. But let's try. I mean, that was a clear mistake. So we're gonna take this and type 192 here. We're gonna remove 64, and hopefully this is right. Actually, I'm not gonna plug it in right now. I'm gonna actually verify this with Desmos, because I'm really not into redoing this problem. Let's find the answer. Desmos won't tell me how to do this problem, but it will tell me the answer. And now I'm gonna type this answer. My answer that I think is the right looks promising, right? 9/16. Yeah, so now it's the correct answer. So I'm pretty sure that will fix the issue. Yep, so we're good. Number 3 is done. Let's do next problem. So we have integral from 0 to 1/4 of arctan of 4x dx. The first thing we're going to do is we're going to set it up as by parts. So my u is arctan of 4x, so my du is 4. So using the chain rule, it is 1/1 plus 4x squared, which is 16x squared, times the derivative of 4x, which is 4, all that dx. dv is just 1 dx, meaning that v is x. So this is my integration by parts setup. So now I'm going to execute it, right? So we have uv, so we have x arctan of 4x, but it's a definite integral, so I'm going to throw the limits of integration right over here, minus integral, but it's a definite integral, so we put this, v du, and we have 4x over 1 plus 16x squared dx. Now, for this one, I'm going to do substitution. My substitution will be the entire denominator. And dt will be equal to 32x dx, and therefore x dx will be equal to 1 over 32 dt. And because it's a definite integral, I'm also going to change the limits of integration. I'm going to go from the limits for x to the limits for t. When x is equal to 0, t is equal to 1. And when x is equal to 1/4, t is equal to 2. So that's my substitution. Now I'm continuing with the same solution, right? It's a continuous argument here, but now I'm plugging in, I'm using the fundamental theorem of calculus, so I throw in the limits of integration. Zero times anything is always 0. So I don't have to write arctan of 0 there, even though it's also 0. And here now we have new integral, but it's in terms of t. So it's going to be 4x, so 4. X dx is now 1 over 32 dt. And in the denominator, we just have t. What's nice about this approach is that I don't have to look up to see the previous line. This solution just flows nicely. Arctan of 1 is pi over 4. Here we simplify, so we have 1 over 8 integral from 1 to 2 of 1 over t dt. Here we have now pi over 16 minus 1/8 ln of absolute value of t evaluated from 1 to 2. So we have ln of absolute value of 2 minus ln of absolute value of 1. ln of 1 is just 0, so the final answer is pi over 16 minus 1/8 ln of 2. Now that we finished the first part of the homework, we are going to try the second part, in which the integrals are not going to be given to us, but we'll have to create them as a part of some application. So in question number 5, we are asked to find the volume using the method of cylindrical shells. And just a quick reminder of how cylindrical shells work. If we have a function on the interval from a to b, and if we take this function and rotate, let's say, around the y-axis, then what we'll get is called the solid of revolution, and we can find its volume using several different approaches, but in this case the cylindrical shells work like this. So we pick some value x, and at this x value we create a segment with width dx, and then if we rotate this segment, what we get is called a cylindrical shell, so that when you cut this shell open, it becomes like a three-dimensional plate, and now the width of the plate is dx. The height of the plate is determined by the parameters of the function, and the width of the plate is the circumference of this rotation. So if we're rotating around y-axis and we take this segment at level x, then the radius of rotation is x, so the circumference will be 2 pi r, but r is x. So that being said, means the volume will be the integral from a to b of 2 pi r h dx. R is the radius of rotation, h is the height of each of these shells. So let's take a look at what's given to us. We have a function cosine of pi x. So cosine of pi x so we have the line x equals 1/2, so x axis, y axis, so it's something like this, right? So we're taking something between 0 and 1/2, and we're rotating it around the y axis, so this is what we get, and it goes all the way here, or maybe not. I guess I need to see it, so let's take a look at Desmos. So we have cosine of pi x, looks like this, and x equals 1/2, so it's this part. Okay, got it. So kind of what I was imagining. So in our case, when we pick this segment of width dx, so our radius is x and our height is just f of x. So this is going to be the application of the cylindrical shells. In this case, so the volume is the integral from 0 to 1/2 of 2 pi x, and the h of x, the height is cosine of pi x dx. And now this becomes our problem. So to do this problem, we're going to use the integration by parts, and we're going to take out the 2 pi, right? This is just like basic maintenance. Let's do that first. We take 2 pi. Now we set up integration by parts. U is x, du is dx, dv is cosine pi x dx, and therefore v will be the integral of this, which is 1 over pi sine of pi x. So that's just a simple linear substitution. So now we have 2 pi, which is outside of the integration process, and here we have uv, so 1 over pi x sine of pi x, evaluating it at 0, 1/2, minus integral from 0 to 1/2 of v du, so we have 1 over pi sine of pi x dx. Plugging in the boundaries, so we have 1/2 sine of pi over 2 minus 0. And here we take out the 1 over pi. Antiderivative of sine is sine of pi over x. It's 1 over pi cosine of pi x with the negative sign. So this becomes positive. And now we plug in these limits of integration here. And 2 pi applies to all of this. So we have 2 pi. Sine of pi over 2 is just 1. So here we have 1 over 2 pi. Plus we have pi squared. And here we evaluate it at 1/2. So we have cosine of pi over 2 minus cosine of 0. And finally, cosine of pi over 2 is just 0. Cosine of 0 is 1. So what we have here is negative 1 over pi squared. Distributing 2 pi over gives us this answer. So this is the volume of this solid of revolution. Let's type it up. So this problem has 2 steps. One is actually setting up your integral, which is we done here, and 2 is actually finding the integral. Now that we know how to do integration by parts, we're well equipped to do both of those steps. Okay, so here we have an integral from, and we actually don't have an integral, so we have to find the area bounded by the x-axis, the y-axis. So here's my x-axis, here's my y-axis, and we have like arc cosine of 4x. And I need to see this one. We're going to graph arc cosine of 4x. And between the so just reading the description, x-axis, y-axis, so we're talking about being bounded like right over here, right? So this is the area like right over here, the one we were talking about. So to find this area, it's basically, so we may want to know this point, this is 1/4 0. Seems like a pretty straightforward setup. If this is my function and I need to find the area underneath the function, all I have to do is just integrate the function on the interval from a to b. This is all everything that we need to know here. So to find this integral, to find this area, we have to integrate from 0 to 1/4. So this is 1/4. And we're integrating arc cosine of 4x. Which now we can totally forget where this came from, and we can just do this problem. And this problem done by integration by parts. So we're going to set it up. And my u is arc cosine of 4x. My du is negative 4 over square root of 1 minus 16x squared dx. My dv is dx, so my v is x. So here we get uv. So we have x arc cosine of 4x evaluated at 0 and 1/4 minus integral, so minus becomes plus, integral of v du. So it's going to be 4x dx divided by square root of 1 minus 16x squared. And the limits of integration are from 0 to 1/4. Now, we've seen this problem before, so I know it's going to be substitution. and my substitution is t is equal to 1 minus 16x squared. So dt is equal to negative 32x dx. So x dx will be equal to, is there really negative? Just want to make sure I found this derivative correctly. And we have negative 1 over 32 dt. And we're going to change the limits of integration. When x is 0, t is 1, and when x is 1/4, t is 0. So, continuing with the problem, we evaluating this using the fundamental theorem of calculus, so it's 1/4 arc cosine of 1 minus 0, that's that, plus, we now have integral with respect to t from 1 to 0 of 4x, but it's not 4x, it's going to be 4 times negative 1 over 32 dt divided by the square root of t. Now continuing, so arc cosine of 1 is 0, so everything is 0 here. We take out the negative 1/8, and now we have an integral of 1 over square root of t dt, but it's much easier to see what antiderivative of that if you just add an extra 2 over here and over here. So now we have negative 1/4, and square root of t is the antiderivative. So we evaluate it, negative 1/4, square root of 0 minus square root of 1. So the final answer is 1/4. Again, we're doing these problems not just for fun, but and out of context, but within a context. And the context here is that this integral represents the area under this function on that interval. Let's try another problem. We're doing the area, and as stated before, this area will be just the integral from negative 1 to 0 of negative x e to the 2x dx. And let's do it. So we're going to set it up by parts. U is going to be negative x, so du is negative dx, dv is e to the 2x dx, so that v will be 1/2 e to the 2x. Again, this is just integration with a simple linear substitution. Here we have uv, so negative 1/2 x e to the 2x from negative 1 to 0, minus integral of v du, but we have that extra minus here, so we're going to put plus integral from negative 1 to 0, 1/2 e to the 2x dx. Plugging in the boundaries into the antiderivative using the fundamental theorem of calculus, so it's 0 minus negative 1 e to the power negative 2, plus, here we have to find the antiderivative, and then we plug the limits, and we're almost there. We don't need this parenthesis here. Plus 1/4. Now we're doing fundamental theorem of calculus here. And we're almost done. Doing like common denominator and everything here, so we have negative negative, 2, so it's minus 3 over 4e squared. Problem number 8. And this is finding the volume. We're rotating about I need to see this one. We have 2e to the power 3x all divided by 7, and we go from x-axis and y-axis, and line x equals 1. Okay, so I see. So we're going to be doing something like this. This is 0, this is 1. We're rotating it around the y-axis, but it's this bottom part that we're interested in, right? So this is hollow here. So we're going to be using the shell methods. So the volume will be the integral from a to b of 2 pi r h dx. But in this case, r is x, and h is my function, and my function is just 2e to the power 3x over 7 dx. So this is my problem. And we're going to do it by parts. So I'm going to let u be 2 pi x, then du is 2 pi dx, dv is going to be, actually, you know what, let's not do it. Like, let's do some, cleaning here before we start dealing with all those u's and v's. So my actual problem that I'm interested in is this. 4 pi over 7 is out. This is all I have. That's it. This is the problem. And we're gonna do it by parts now. My u is x, so du is dx, dv is e to the 3x dx, so that v is 1/3 e to the 3x. Now we have 4 pi over 7, which is not part of the integration, but here we have uv, so 1/3 x to the power times e to the power 3x, evaluated from 0 to 1, minus integral from 0 to 1 of v du, which now gives us this pretty straightforward path to the final answer. Evaluating it at 1 gives us that. Evaluating it at 0 gives us 0. So there isn't much going on there. Minus, here we have now 1 over 9 e to the power 3x from 0 to 1. And 4 pi over 7 remains outside of this whole integration. We have this, and we have 1/9 e to the cube minus e to the 0, and this is just basic simplification, 4 pi over 7 e cube over 3 minus e cube over 9 plus 1 over 9, 4 pi over 7. We have 2e cube over 9 over 9, so plus 1, and maybe one more tiny thing. It's just 4 pi over 63, 2e cube plus 1. Four pi parentheses 2e cube plus 1, all that by 63. And we finished it. So if you have any questions about doing integration by parts with definite integrals, please feel free to reach out.